Hello everyone, welcome to Chapter 2. We are looking at how to summarize data here, and we have several ways of doing it. So we'll begin with frequency distribution, and then we will move on to histograms and other ways to summarize your data. Because you must understand that when you have large data sets, right, you have plenty of entries, values. So it's just called raw data. It is raw in the sense that it is not meaningful as yet. To make it meaningful, we have to have a way of summarizing the data and making it more manageable. And the first step is to talk about frequency distribution. Okay. So what happens here is the need for this is when you have large data sets. So let me write that here. Helps summarize large data sets. This is a way of organizing the data and it helps us to understand the distribution of a data set. Now in math, especially in algebra, we've learned about how different equations would represent different families. For instance, if you had a linear equation, right, a linear function, y equals mx plus b, or ax plus by equals c, these are two ways in which an equation can appear for a line. And you know that when you have an equation that fits that format, that template of a slope-intercept form or a standard form, you know that that's going to produce a line. The shape that you will see on the graph will be a line. Likewise, we've learned about quadratic equations, y equals ax squared plus bx plus c. Quadratic equations would always produce a parabola. So when you look at the equation, you can predict the shape of the graph, and vice versa. When you look at the shape of the graph, you can predict what family it comes from, right? Similarly, when we organize data, we are able to understand, based on the summary there, as to the nature of the distribution. And just like math, we have different shapes that produce, indicate different distributions. So we have normal distribution, binomial distribution, Poisson distribution, uniform distribution, and so on. So they are again separate families and they behave in a certain way. Of course, they have requirements, and if we meet those requirements, and if the shape of the distribution, matches with the known ones, then it makes our life so much easier because then we have something to work with. And it helps us to also understand what the population could be, how the population is distributed, and so on. Okay, so this is basically a table. You put it as a table, and what you put on the table, if you are able to put it on the graph, then you begin to see the shape of the distribution. So we're going to do both those things here. Okay. Now, in order to define this, I'd like to provide with you a list of definitions first, and then we will go ahead and do an actual problem. Okay. So I'm going to give a formal definition for frequency distribution here. Okay. So I'll say also known as AKA, also known as frequency table. And here's the definition. So let me read it first and then I'll write it down. So it shows how data are partitioned among several categories, or we call them classes here, by listing the categories along with the number of data values in each of them. I know it sounds lofty, but that's the formal definition. Let's put that down and then we'll come back and look at it more clearly. Okay. And here let me go over this one more time so we can try to understand at least to some extent what we're talking about. Now remember, we're talking about building a table, and we call it the frequency table. So think about the word frequency. In plain English, frequency is how frequently something repeats, right, or occurs. So frequency table is helping us to summarize this data into several classes, or you partition the data into several classes. when we say classes, that's the technical name we use here. It's basically intervals. Okay, so for instance, if we have a data that has the height of all the high school students in a class. Now let's assume that the height is measured in feet. So we have the heights of these high school students. So you have that raw data. So if I could summarize it in such a way that I could say, okay, 4.5 to 5 feet, how many students are there? If there are none, then 0 would be the frequency. If I can find like say 2 students, then the frequency would be 2, because that's how many students fall in that category or in that class. Then I could go from 5.1 to 5.5 and so on. It just depends on how we want to categorize. In fact, there is a way in which we do it. And so that is what we mean here in a frequency table. So this raw data that you have can be summarized nicely if I can have these classes or categories, and how many in that data set fall in each category, so that when I add up the frequencies, meaning if I add up how many fell in each category, I will get the total number of those high school students whose heights were measured. So again, it's all verbal for you right now. I will show it to you through an example, but as I mentioned, we have to write some definitions to understand that language, so I can call upon that terminology when I build the table for you. Okay, so please bear with me as I put up the definitions. So we have some terminologies here, and I want to use this example to explain what they stand for. Okay. Now this is called a grouped data, because what I did was, as I mentioned before, this would be the height of those high school students measured in feet. And so we have 4.5 to 5, 5 to 5.5, 5.5 to 6, and 6 to 6.5, right? So what happens here is we have this data that we have, built it into an interval, and we found the corresponding number of students who fell in that interval. Okay, the frequency stands for how many students fell in that category, right? So the lower class limits, okay, what is the lower class limits? The lower class limits refers to these ones, because in each class, that's the smallest number that belongs in each class, right? So that would be the lower class limits. So obviously the upper class limits would be these ones. Okay, so those will be the largest numbers you can find that belong to each category or each class. Okay, class boundaries, what do they stand for? These are the numbers. These are numbers that we use to separate the classes, right? So each class is separated, right? 4.5 to 5, then 5 to 5.5. So we separate these classes without the gaps created by class limits. Okay, because if I say if I went from 4.5 to 5, and then I went from 5.1 to 5.5, then between 5.0 and 5.1 you have infinite possibilities, right? 5.0 to 5.1, because you could have 5.01, 5.001, 5.00001, 5.02, and so on. So you have plenty of values that could be there, isn't it? So to avoid that gap, when you switch from one class to the next, we kind of use class boundaries to separate them and not have any gaps. Okay, and then we have class midpoints. As the name suggests, this is the middle value of each class. So if you want to find the midpoint of the first class, let's say 4. So how do you find the midpoint? You add the lower limit and the upper limit and divide it by 2. That is how we find the midpoint, right, between two values. So the lower limit is 4.5 for the first class, and the upper limit is 5.0 for the first class, and then you divide it by 2. Okay, so then you can see that this is 9.5 divided by 2, and then go ahead, use your calculator, and it comes out to be 4.75. So the midpoint for the first class would be 4.75. Why would we need it? there are two things. If you see this as an interval, you can see that it's a range of values, isn't it? But if we wanted just a single value to represent that class, then we could use the class midpoints. And when we get to that, there is a reason, or there's a place where we'll need it that way. And that's when we will convert all of these to the midpoints. Okay. So for instance, if you want to compute the next one, okay, so 5.0 plus 5.5 divided by 2, you will get 5.25. So this will be 4.75. I'll just say midpoints. Okay, and that gives us 5.25. Then try and compute the next one. You could actually pause if you wanted. And then you divide it by 2. Add the 2 and divide it by 2. You get 5.75. Then go for the next one. And you can see that, there is a pattern that you can begin to see, right? In fact, you could actually figure out what the next one will be. 6.0 to 6.5 would be 6.25. And you can see that pattern, right? 4.75, 5.25, 5.75, 6.25, and so on. And so that it's because of the consistency there that we like it. Now, what about class width? Class width, as the name says, the width or the difference between two consecutive lower classes. Okay. So what does that mean? So I'm going to group these two and point it to you here, because that will be your class width. So I'm taking the consecutive lower limits. Okay. So the difference between them. So I have 5.0 minus 4.5. That gives me 0.5. Okay. So that is the class width, because each class has that width of 0.5, and that's kind of visible, right? You can see that. And then it should work in every consecutive pair. So that will be 5.5 minus 5.0, which is 0.5. And of course, you want your class width to be the same so that it's all uniformly arranged. All right, now let's go ahead and look at an actual problem and then try to build this frequency distribution. Okay. Let's take a look at this raw data. This data is related to the drive-through service times. Okay, this is during lunchtime. So this is McDonald's drive-through service time, and it's measured in seconds. So how long does it take to serve in the drive-through during a lunchtime? Okay, so you must understand that because it's lunch, it's got maybe more food types to serve. So this is their data. Now this is a raw data for the fact that it's just a collection of all the service times, right? So why don't you go ahead and count how many there are? So if you go ahead and count it, it gives you an idea of how many entries there are. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 times 1, 2, 3, right? So go ahead and do that. You get 51, but this last cell is empty, right? So we have 50. So the number of entries is 50. Let me just write that here. Number of entries is 50. Now we need to summarize this data in a sensible way so that we can begin to see the distribution. We saw previously that if we could put it in a table, a frequency table, and get those classes or those categories, then it's easier for us to look at the data and see how many people were served between this time to this time, and so that gives us a better idea of their service times, isn't it? So how do I first decide what goes in each class? How do I decide what the lower limit must be, or the upper limit, or how do I know how many categories? Because this one has 4, right, in the example here. This has 4 categories or 4 classes. How many classes should I build here? So for that, we have a procedure, the number of steps that we will follow. So let's start with step 1. Okay. Now this is a manual way to do it, and it's really important for you to know how to do it so that you will know how to translate that in your calculator, so that the background knowledge helps you to decide what to do. Okay, because just because there's a calculator doesn't mean it's going to do everything for you. It's what you input that it's going to give you back as output. So if you don't know what to input or to even understand if that's a meaningful input, then whatever it responds to that entry, we'll blindly accept it, right? So here we go. So step 1 says select your classes, the number of classes between 5 and 20. Okay, so remember 20 rows, 20 classes. So 5 classes means 5 rows of data, or 20 rows. So we have 50, so I feel like we should go with 5. Okay, so again, when I say I feel like, it's just because it sounds convenient. If it doesn't work, then try 6 or 7, but 5 seems to be the most desired number of classes. So I'll just say we go for 5 classes. Okay, because you need to have a very large data set to go all the way up to 20. Otherwise, you break it down so much, you really can't see the pattern. So you want to be reasonable in the way you break down your data, or you separate or partition your data. Okay, so we've selected step 1 for to be 5. Okay, so we're going to have 5 rows, 5 sets of intervals. Step 2. Step 2 is where we calculate the class width. So this is the general formula that we will use. Okay, I put approximation symbol because you might sometimes get decimal answers, and if you don't want that, you just want a convenient number, right? You want your width. Like in the previous example, the width was 0.5. There it made sense because you're talking about the height. You can't go from a whole number to another whole number because you'll be bunching them up too much. So especially it was a height of high school students, so that's the age where they grow. So it really matters, in terms of how you break it down. So the decimal there makes sense. And also it's an easy decimal. 0.5 is easy for us to partition it. So anyways, coming back here, this will be the maximum data value minus the minimum data value divided by the number of classes we chose in step 1. Okay, and so this is the general formula when you do any calculation for any data set, when you calculate the class width. So let's come down here, and for our problem, go to your data set and find the largest number, okay, the highest number. So you have to scan through your data to find that information. Okay, so we have the hundreds, and we have the 200s, and we have some in 2 digits. So you know that 200 seems to be the higher one. So see if you can find anything in 300s. If you do, then you want to look for anything else in 300. So I see that I should use a different color. 308 there, right? 308 seems to be the biggest number there. And then we saw 2-digit numbers, so we know that that has to be the lowest. So we have 91, 90. See if you can find anything smaller than that. Yes, there's an 83. So then we come back and say, okay, my maximum data value is 308, and my minimum data value is 83, and the number of classes I chose was 5. So use that, and that gives you, actually it gives you a nice number. It gives you 45. But again, remember, you can always round. This is just a general idea, okay? So you can always round it up to a more convenient number if you want. So I'm going to round this up to 50. So I'll just say round up to a more convenient number. So 45 looks fine, but you have to, what it means is you're going to divide or break your classes, the widths by 45, and that can get really 45 plus 45 plus 45. Instead of that, if you did 50 plus 50 plus 50, it's a little more intuitive. That was the reason for rounding it up to 50. So then we go to step 3. Okay, the general rule in step 3 says to choose your first lower class limit, right? Remember what we mentioned, so let me take you back quickly. Lower class limit is the red one here, right? So these are the lower ones. So the first lower, 4.5, how did they choose 4.5? So that's the part we are here in. So we're trying to choose that first lower class limit because that will set the tone for the rest of the values. So we can do this in two ways, okay? So you can choose the lower class limit by using the minimum data value from your data set, or you could go for a convenient value below the minimum value. The reason again is to give it better coverage, right? It's more conservative. So if it's 83, you want to go below to 80. You don't want to, if you don't want to start at 83, because remember, if it's 83, then you have to add your class width to it. So 83 plus 50 again would give you not a round number. When I say round number, I'm talking in terms of convenient rounding. So for that reason, we want you to go below as much as possible, because it really doesn't hurt, because there's not going to be any value below 83 in this case in our data set. So we are not hurting by going below, but we will hurt if we went above it, because then we will lose that 83 value, that the frequency for that, right? So what we're doing here is for our problem, so I'll just say lower class limit, okay, LCL. So we know that the minimum value is 83, and if we want to choose a convenient value, I can go for 80, but I'm going to choose 75. Okay, 75, so that I could keep adding the class width to the 75. For that, you should also kind of look at your data spread. Okay, so so then I'm just choosing 75. You could choose 80, no problem. You can start at 80 and then keep adding your class width to it, because that is the next step. Okay. So when we have this 75, the lower class limit helps you to build your, use this lower class to list the other lower class limits. So that will be step 4. Use the first lower class limit of, I'll just write the general version, 2 lower class limit and class width. So basically using step 3 and step 2 here, right? Step 3 and step 2 to list the other lower class limits. So what happens here then is, for our problem, then I will start at 75, right? So 75 is my first number because I chose to go with a convenient starting point, 75. So I have to keep adding the class width, which is 50, right? So 75 plus 50 will give me 125. So I'll just write here that 75 plus 50. And then now this is 125. So I have to do 125 plus 50 to get the next lower class limit, and that will be 175. Then I will use 175 plus 50 to get the next one, 225. Remember, I'm trying to build 5 classes, right? Because that's the number of classes. So 1, 2, 3, 4. I have 4. The next one should be the 5th one. Okay. Because I know that's 225 plus 50 will be 275. So we get that by adding the class width to it. Okay. So I'm just going to remove that so that you can see that this is your list of lower class limits. Okay. Then of course you have to now go to step 5. Says determine the upper class limits. We'll call it UCL, upper class limits, for each class. So for our problem, then it's going to be How do we determine that? We just simply have to now add a 50. Right? And moreover, what we can see here is if it's 75, right, and here it's 125, so you want to stop one before that. I'll talk about how we need to fix the boundaries later. Okay, remember here it ended at 5.0 and then again started at 5.0. So we want to make sure that that happens, but before that, I'm just trying to categorize it. Okay, so here I don't have any decimal values in my data set, so that means I will not lose anything in between, right? For what I mean is, I'm going to take this LCL here, just repeat it here. And for the upper class limit, I'm going one less than the lower class limit in the next class. So this is 124. There is a gap between 124 and 125, right? What if you had 124.1, 124.3, 0.7, and so on? Now, if we look at our data, we don't have that issue just because your data sets are whole numbers, right? We don't have any decimal values. But remember, we will take care of that gap later when we talk about histogram. But for now, we are just building a table. So this will be one less than 175, so that's going to be 174. So that's going to be 224, 274. And how do you finish off the last one? The last one would be, if you added another 50 to this, right, the last one, that would give us 325. So we'll stop at 324. That's how you know where to end. So now go back quickly and look at your data set. Do you have any value exceeding 324? You can look at your data set, but you also did that in step 2 when we chose the maximum data value, where we figured the maximum value is 308. So our class, the last class, will accommodate the highest value comfortably, right? Because we want to make sure that we have adequate number of classes to cover and accommodate all these values. It is kind of inbuilt in these steps. You will, it's kind of assured that you will find that, but you always want to cross-check it, never give it a chance, like that, okay? All right, so we now have built our classes, our categories, right? So we have now categorized or partitioned our raw data into these intervals. So now let's go to step 6. Take individual data value and put a tally mark in the appropriate class. Then add those tally marks to get the frequency. Okay, so for our problem, then we will have so we're not going to write LCL and UCL in our table, but we're going to say instead the time in seconds, right? The service times. So let me build that table here. You always want to say how it's measured, because what if it was in minutes, right? Or hours? It's a frequency table, so the column is called frequency, right? So now we have 75 to 124, 125 to 174, 175 to 224, 225 to 274, 275 to 324. Okay, so now we have to go to the data set here and look for all the values between 75 and 124. Okay. So you need to have the data set close by to do this. Okay. So maybe I'll bring the data set closer to that step. Okay. All right. So I have brought the data set closer to our table, so you can see that now. So now we're going to mark, the tally marks for all these values. So there are several ways to do this. Tally mark is the traditional way we do it. Because we are doing now using digital tools, let me try to highlight the ones that fall in that interval. So between 75 and 124, all the values that fall in that interval is what I'm trying to mark. Okay. So you can go column wise if that's a quicker scan for you. Okay. So 124, so I have that. Right. This is within 124, between 75 and 124. So then I have that. So I want you to go ahead and do that. Okay. I went ahead and marked them all. What's nice about the digital version of this is, when I was a student, we had to kind of cross it off and do it manually on a piece of paper. But now it's easy when I highlight it, so that at the end of the entire table, if I've highlighted them all, I know that I took care of all of them. So if you didn't have that ability, you can always score it off as soon as you've accounted for a number. So when we see tally marks, this is how we do it, right? So each number you get, 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then 1. So I have 11. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I know I have 11 there. So the frequency for the first one is 11. Okay. Now go ahead and do that for the next class, 125 to 174. Okay. So again, do it similarly. If you wanted, you could use different markers to color them, or you could, so that you don't get mixed up with the ones you've already counted. So it's your call, but pause your video at this time and complete the table yourself. Okay. Now remember that there is a way to understand how this works. Let me use a different color then. There's a way to understand how this works, because once you have completed your table, and if you added your frequency column, you should get 50, because there were 50 entries, right? Total number of entries in this raw data was 50. So that way you know that you accounted for all of them, didn't duplicate them or undercount them. Okay. And this is number 11, not 2 tally marks. Okay, it's 11. It's just worked out that way. So let's check to see if this is what you got as well. I did use different colors. I literally ran out of colors, but the colors kind of helped me to count them, so that I didn't count the ones that were already colored. So using different colors helped me personally in accounting for it, and it made my process much more smoother, I would say. All right. So now what happens is you want to quickly check if you took care of all of them by counting this. So add all these up and you get 50. So you know that you did account for all of them. Also, the color, the shaded colors help me to verify that as well, that I took care of them all. I didn't repeat them or add them twice. Okay. So that is how we do a frequency table. This is a distribution, okay, that we use. Now, there are other ways we could do this, in the sense we could use this distribution to discuss, what we see here and so on in a different pattern. So I'm going to show that here. However, the best way to translate this distribution into, this table into a meaningful distribution is to use histogram, which I will be doing shortly. So I would be using this information, the same table. So if you're taking notes, I want you to understand that this table will be used as a theme to discuss the problems, the concepts, related to this problem. Okay. So for now, I'm going to quickly talk about relative frequency, another way we could utilize this table. Okay. So let me write that out here. So this is frequency table, but you could convert this into a relative frequency table. And what happens is this is also known as percentage frequency table, because that's a quick way for you to recognize that it's a collection of percentages. Okay. So let me write that here. There's a relative frequency for a class. So you're going to do that for each class, for a class. That's a formula. So you take the frequency of the class, frequency of a class, and divide it by sum of all frequencies. So let's go back to this table here. The frequency of a class, let's look at the first class. Okay, the frequency there is 11, and the sum of all the frequencies is 50, so it's 11 out of 50. Okay, that will be the relative frequency of a class. Percentage of a class, because it's called a percentage frequency table, we understand it better, is you take this formula and multiply it by 100%. You just convert that fraction to a percentage. So I'll just write that here, frequency of a class divided by sum of all frequencies times 100%. Okay. So we're going to take this current problem and convert it to a relative frequency table. Okay. So let's do that. So your class will remain the same. Okay, so I'll just say time in seconds. Okay. And instead of frequency, I'll call it relative frequency. I'm going to create one more column for the percentage. Okay. This tells you in relation to the total, what was it for each class. Okay. As you can see, I have the times recorded here. Now I'm going to do the relative frequency. So if you go back here, it was 11, 24, 10, 3, and 2, right? So the first one would be 11 out of 50. The next one would be 24 out of 50. Remember, it said frequency of that class divided by the sum of all frequencies. The sum of all frequencies is 50. And the next one would be 10 out of 50, 3 out of 50, and 2 out of 50. So technically, if you added these, then you would get, well, this is a symbol for adding them. Okay, so this is like an E, but it's actually a Greek symbol. We call it the sigma symbol. Here we'll call it the summation symbol, but it's sigma. Okay, there are two sigmas, lowercase and uppercase in Greek, just like in English. So this is a sigma symbol. That means summation. So it's usually summation of what? Summation of the relative frequency table. So if you added them all, because they all have the same denominator, you simply add the numerators, you should get 50 out of 50. That means you took care of all of them. You didn't miss any of them, right? So we have that. So if it's percentage, then you know that this column would be 11 out of 50 times 100%, right? So again, feel free to use your calculator, you want to write it the way you see it exactly. So basically, this 50 and the 100 will cancel each other. So 50 and, let me show it this way. I'm just trying to show you to do this manually so that you don't have to rely on the calculator every time, but you'll still be able to. 50 times 1, 50 times 2, right? So basically, it's 22%. Let me write that here. Likewise, 24 divided by 50 times 100% would be same thing. 50 and the 100%, the 100 would cancel off twice, and so 24 times 2, 48%. So go ahead and do that for each one of them. So that will be 20%, 6%, 4%. Once again, add all of these. Okay, summation percentage. So again, pause the video at this time. If you feel it went too fast, go ahead and do this. Okay. Another way to do this is the simplest way, because you don't have to use a calculator. If I cross cancel them, it's just basic math. You are pretty strong and familiar in that. Otherwise, you wouldn't be here. So we have 24 over 50. If you are not sure, then you can go ahead and use a calculator and do 24 divided by 50. It gives you 0.48. Then multiply that by 100, and then you get 48. So you still can get it done. If you didn't use a cross cancellation, you can use your calculator to get this. Anyway, so go ahead now and do the last column by adding them up. So 22 plus 48 plus 20 plus 6 plus 4. What should you get? Because it's percentage, it should all add up to 100%. That means we took care of all of them. And that is how we use the relative frequency. What's interesting here is you can see that nearly 50%, 48%, right? Nearly 50% of the service times fell between 125 and 174 seconds, right? And that's valuable information. And if you look at the last one, 4%. 4% of the time of the services took 275 to 324 minutes. So that's really, really long. And so they can go and actually investigate to see, was it a large order that maybe required this much time, or was it a specific employee who served those at those times, and perhaps that employee needs training. So this is valuable information for the organization to really develop their standards and maintain their standards, and see what went on, if it's legitimate that the order was really large, and so and it's only 4%, so it is likely that the order was really large. Or it could be a new employee or some employee who wasn't keeping up with the expected timeline, and they were delaying for whatever reasons, and they need to be retrained. All right, so it gives you that information here when we do the relative frequency. If you had, say, sometimes, and this was convenient for us because of the 50 in the denominator. If you had, say, 49 or something, right? If you had 49 entries, then your fraction will be a little messed up, in the sense you'll have more decimal numbers. In those cases, what we say is, if that's the case, when you add them up, it may not show up 100%. It might show 98%, something off, slightly off. So those are rounding errors, because you had those fractions that wouldn't really come out nicely without decimals. So those can be, given a little wiggle room, because you're rounding those errors. Okay, so it should always come up as 100%, but if it's slightly off, see if it is supported by the fact that your fractions had rounding errors, because you had those multiple decimal places. Okay. The next outcome of this frequency table is we could adjust it to build a cumulative frequency distribution, or cumulative frequency table. And if you see the word cumulative, it sounds, you know what it is, but a quick way to remember is accumulative, right? Accumulates. So it adds up, accumulates. So cumulative means to add up to what is previous, right? So that is the whole idea. Here we have so I'll just say accumulates. Accumulates, or in this case, it's a sum of frequencies for that particular class that you're focusing on, for that class, and all previous classes. Now our final exam will be cumulative. What does that mean? That means it's going to take all of the past or the previous chapters we've learned into account. So it's not just the last chapter, say chapter 13. That's not going to be the only one on your exam, of course, right? So that will be part of your exam, and so it's that chapter, the last week's chapter, chapter 13, and all the previous chapters. So that is what we mean by cumulative. Okay, so let's go ahead and write the table again. So time in seconds, Again, for convenience, I'm going to bring that frequency we used. So that's easy for us to see the adding. And then I'll call the last column as cumulative frequency. Okay. As you can see, I have filled the columns. So this was what we started with, right? Now we go to cumulative frequency. The first one will be 11 itself because you have nothing previous to it to add. To get the next value, so you're going to take this 11 and add 24 to it. Okay, so go ahead and compute that. So that will tell you we have 35. Then take that 35 and add 10 to it. Let's put the 11 here. Alright, so that's going to be 45. Take the 45 and add the 3 from here. Do you see what I'm doing? So we have this 11. Sorry, not that one. How do I show this? Okay, 24, 10, 3, right? So to the previous one, you're adding the current frequency. So 45 plus 3, 48. Then 48 plus 2 is 50. Do you know you did that right? Because it should all add up, cumulative. So it should add up to 50. So this is really interesting because now you have a way of seeing what happened all the way from the start of, I mean, the 75 to 124 is the lowest, the starting class, right? So then you can actually rewrite this information as that it took less than 125 seconds, right? So it actually means all the way up to 0. So, okay, no time, 0 to 1. It doesn't matter because although your class starts at 75, there were anyway no values in your data set below 83. 83 was the lowest. So you can simply slash it all down and say less than 125 seconds. So 11 customers were served in less than 125 seconds. Now that is a lot more meaningful than having those intervals, right? And what would this be? The second one is a cumulative one, 35 this side, right? 35 here means these two together because it's a sum of a cumulative frequency for the two classes. So you can simply say less than 174, which includes the first class, right? So less than 174 seconds means all of it below 174, all the way from 0 up to 174. So which means it's including the previous class. And what this means is we can say, well, 35 customers were served in less than 175 seconds at that particular drive-through McDonald's restaurant. So that you can go ahead and do that here. Basically, that's what I'm trying to show you here. For the third one, it will be all three of them. So that will be less than 224. This would be less than 274, less than 324. So if you look at the last one, less than 324, all of the customers who used that drive-through service were served less than 324 seconds. They served in less than 324 seconds, or 325 you can say, okay. Because I kept doing the lower class limits, so sorry about that. It should end with a 5 because that's what I was trying to do. You always want to do that because, you know, the first class ends at 124. So if you say less than 124, that would mean if someone was served exactly 124 seconds, then they wouldn't be counted in that, right? So you go one above. So you always use the next lower class limit safely. So 125, less than 125 would mean all of them in the first class. Less than 175 would mean all of them in the first and the second class, and so on. So it was something I had to fix. So you use the one higher than the end of that limit. Okay. All right. So that is your cumulative frequency that helps you with these with the interpretation of this cumulative frequency. So it helps us to really understand that how many were served. The previous table, the relative frequency, shows you what percentage of people were served, but here it shows you how many were served, and that is also helpful because only 50 service times were recorded in that data set, so you are only talking about those 50 values. All right. So then I'm going to now talk about the application of your frequency table in terms of understanding what kind of distribution it follows. Histogram. Okay, it's a strange sounding name. It sounds kind of ancient. It's history or something like that. But what you can see is histogram is a name that's given to this particular tool that helps you to graph and interpret the table of numbers. So this is basically a graph for frequency distribution of frequency table. Okay. And this is a graph that consists of bars. It's a bar graph. Okay, it consists of bars of equal width, because you don't want one bar to be slim, another one to be wide, so you want all the bars to be of equal width. And we took care of that, right, because we had the class width, so you do have that taken care of there. Okay. And these are drawn adjacent to each other, right next to each other. These bars have no gaps. That's really, really important. And this is the reason, or this is the place where we will talk about class boundaries and all that, because if you see here, 124 and 125, there is a gap there, right? So when you're drawing these bars, there will be a gap because you'll have to jump from 124 to 125. So a histogram requires that there are no gaps, okay? So I'll just say bars have no gaps. And this is so crucial because it's because of that that we will use the boundaries, class boundaries. And we have, of course, because it's a graph, we have the x-axis and the y-axis, right? So in this case, the x-axis or the horizontal scale will correspond to the classes, okay? And the vertical scale is nothing but the height of your bars, right? And the height of the bars will correspond to the frequency. So classes will go on the x-axis and frequency will go on the y-axis. But in our particular problem, your classes will be the time in seconds, because those are your classes, your categories. And frequency, we called it the frequency, but frequency here would be the number of people who were served, right, for those corresponding times. So what is the importance of the histogram? Okay, histogram, the importance is that it helps us to visually see, or it visually displays the shape of the distribution. Okay, remember how I said when we have a linear function, if the function comes to us as an equation or as a table, we can't really see what it is. But when you graph it, you get a line, so you can see, you have a visual shape of that function, right? Likewise, you can have a table of values, and only when you graph it, you will know if is it a line or a parabola or a chair-shaped graph or whatever shape it tends to take, right? Exponential, logarithmic. So we have a way to categorize it only when we see the shape. When it looks just in the tabular form, the table form, it has its own uses like we saw before, right? We were able to see how many were serviced in what times and what percentage and all that, cumulative. So there are advantages to the table, but we want to see the distribution, then we have to use the histogram, which is the graph of those frequency tables. It helps us to locate it shows the location of the center. Let me finish this, distribution of the data. It shows us the location of the center of the data. when we draw a histogram, it will help you to see what we mean by that. It shows the spread of the data. It helps identify outliers. Outliers, as the name says, these lie out of the general data set. So these can be extreme values, extremely small or extremely large, and they do not fall within the reasonable limits of your data set. So it could be a human error, a data entry error, or it could be something that is really there, and some unique circumstance. For instance, let's take a classroom. Typically, if a classroom has students with an average age of, say, 25, you might have once in a while some students who are in their in their 80s, let's say, right? And that's happened to me too. We've had students who joined college in their 80s, and they graduated successfully, and it's always been an inspiration for me, to see them, because there was this sweet lady who said, well, now my husband passed away last year, and I've been caring for him for 15 years because he was bedridden. So I had all this in my bucket list, but my priority was to be there for my husband. And now that he's no more, I've returned to fulfill all the things that I wanted to do. And she said, this was very big on my list, and so now I have joined college. I was so amazed, so thrilled. I was so honored to be her instructor. Anyways, I went a little off there. Coming back here. Now, in the class of an average age of 20, when I say average 20 or 30, let's say 30. When I say average, I mean that in general, if you added all their ages and divided by how many people were there, that would be the 30. Doesn't mean every person there is 30 years old, right? You will have some who are really young, some who are meaning they're still in their high school taking college classes, or you could have people in their teens, in their early 20s, but whatever it could be. If you had an average age of 30 in that class, and if you had, say, 2 students who were in their 80s, that is going to drag your average to something bigger, right? Like 60 years or something. It will say, oh, the average age of this class is 60 because you had these 2 outliers who were not the typical in the typical age range of the class. So then we have to go and investigate, did somebody punch in those numbers as 80 accidentally, or did we really have students who were 80? So that is important to verify. So it helps us to identify outliers. Okay. So these are the big things that we will learn from the importance of these of the histogram. All right. So now let's go ahead and try to get the histogram marked. So for that, I'm going to first write the table. So what you see here is, in order to build my histogram, I cannot use my table values as it is because of this issue here. Our histogram specifically says there should be no gap. And we have the gap there because you have that 124 and 125. So when you build your histogram, there will be that gap. So we need to take care of that gap by getting or translating our classes in using class boundaries. So we want the boundaries to match, right? The 124 and the 125 should match. Now I cannot put that 124, turn that 124 into a 125, because then you wouldn't know, if you had an exact value of 125, you really wouldn't know where to throw it, right? Should it go in the first class or should it go in the second class? So for that reason, what we do is we use class boundary concept, which basically takes the difference or basically takes the midpoint of these endpoints, and then that will help you to build up your not the midpoints, I should say. Let me just show you the calculation here. Okay, so I take that 125 and subtract the 124 from it. Okay, and I will divide it by 2. So that is going to be 1 divided by 2, which is 0.5, right? So what I'm going to do is I'm going to take away half a point from 125 and add that to the 124, so that my class boundary would look like this. Okay, 75 to 124.5, and this will be 124.5 because I took away half a point from 125. That makes it 124.5, and I will throw that extra half to the 124 in the previous class. Now, because the way it is ending, I'm going to change the 175 or the 75 also to 75.4. Again, remember, this is the lower end. It doesn't matter. We took a convenient number, and again, remember, the lowest data value was 83. It doesn't hurt us to go from 75 to 74.5. We wouldn't be losing or missing out on any value. Okay, so we do the same thing for 174 and 175. So 175. So the upper class limit from the next class minus the lower class limit from the I apologize. The lower class limit from the next class minus the upper class limit from the previous class divided by 2. And you notice that it should always be that same way because of the way we set up, right? We use the class width. That's how we built our lower class limits first, and then we built our upper class limits based on that. We're going one less than the lower class limit from the next class. So because of that setup, you'll always have that 0.5, and so you're going to throw that 0.5, distribute that 0.5, so that 174 gets an extra 0.5, and 175 here loses a 0.5, so it becomes 174.5. What this does is, of course, it helps us to keep that these ends matching, right? So we want these ends to match so that there will be no gap when we draw the graph, and that is the way we build our class boundaries. So 224.5 to 274.5, and then we have the 274.5 to 324.5. All right, now it's time for us to go ahead and draw this on a grid. 224.5. Let's stretch this some more because that won't be enough. To 74.5. And then we have 324. Right? 274, 324. So what I did was I went from the first lower limit all the way to the last lower limit, jumping by 50s, right? So I did 75.5, 124.5, 174.5, 224.5, 274.5, and then ended with 324.5. Okay. Now on the y-axis, remember the x-axis refers to the classes. In this case, it was time in seconds because we had a context. In general, we would call them classes, but when you have a problem given in a context, then you want to use that information, which is service time in seconds. Now, the y-axis, we are told, should be the frequency, right? And so we have, again, our values. If you go back to the frequency table, our values range from 2 all the way to 24, right? That's the lowest value, 2 all the way to 24. So to be able to accommodate all of these values, you can choose to jump your, mark your scale by jumping in 5s or 2s. So I'll perhaps jump by 5s, okay? So I'm starting at 0, 5. You know, you should always start at 0, but remember I gave you that little squiggly thing because that is a way for us to say, okay, you know, this is happening far away from 0. But we're trying to see it closer, so I'm kind of squishing them all to the left. 5, 10, 15, 20, 25, because the highest value was 24, so that should accommodate it, right? All right, so the first class had a frequency of 11. So we have, over this interval from 74.5 to 124.5, this width here is up to 11. So it is as if you draw a bar. Remember we said it's a bar. So I'm shading the bar like this. Okay. The height of the bar is 11, right? So that corresponds to the value 11 here on the y-axis. So you don't have to write the 11, but I'm just writing it there so you can see. because I'm kind of eyeballing the position for it. Then the next class has 24. So remember, these bars must touch. So 24 could be one below this. So I want to bring it all the way here. It's 24. So it's a little here below this, and shade that. And see how the bars were touching because we used the class boundary. The next one is 10. It's kind of easy because it's exactly at 10. If you do it on a graph sheet, you know, the width will be perfect. Right now it's looking good, but you'll make sure that it's perfect width, because the bars should look the same size in terms of the width, right? So mine could look a little bigger than the others. It's just because I'm not using a perfect scale here on a grid. Then we have 3 and 2. So 3, see, this width is really looking a bit wider, and then 2. So just for us to remember what we did, 3 and 2. So you can see the distribution, right? You can see visually how it appears. So it helps us to see the display of the shape of the distribution. And we also will get other details from it. So when we get to it, I will talk about it. But meaning the center and the spread, I can give you a rough gist of it. The center is usually the peak of the graph, okay? So the peak, and the spread of the graph is how wide the distribution is. Is it narrow or is it spread out? So you have the idea of the center and the spread, because remember, those were the things we said under the importance. Okay. We identify any outliers. So if you have the distribution and something way at the end, in this case I would think of 2s as the outliers in a sense, because it took really long to service 2 out of the 50 you know, in that time interval. So we have all these things here that we can use to define our histogram. Okay, now we have this is a nice shape, but sometimes you can have different kinds of shapes. So we have different distributions that can look differently. Okay, so we will talk about that quickly. Oh, before I go to the other common distribution shapes, I just wanted to highlight to you that you know, let me take you way back. We did the midpoint, isn't it? I kind of discussed that way in the beginning. So you have the midpoint. I think I gave that information in these examples here, right? Midpoint, yeah. Class midpoints, and I showed it to you here. You take the average, or you add the lower limit and the upper limit and divide it by 2 for each class to get your midpoints, right? So what we could do is, if you didn't want to see it as bars, meaning you can modify, a histogram should always have the bars, but you can modify it to draw a frequency polygon, or, you know, we call it frequency polygon if you took the midpoint of the distribution, right? So, so for the first class, it is 124.5 plus the 74.5, which is, and then divided by 2. Right? So that will be 99.5. So that's somewhere here, right? 99.5. So that will be the midpoint here. So likewise, you can find all the midpoints, isn't it, for each bar. So if you remove the bars, you just have those midpoints hanging there. And what we do is we usually connect them, connecting the dots. So this kind of gives the shape, the distribution. So if you remove the bars, you can kind of see it's like a mountain, right? With the bars also you can see that, but if you remove the bars, the width of the bars are not distracting, so you can actually see where the peak is and where it goes down low, and so on, right? So we want to, we can use that information to build it. Now if you had you know, continuous distribution, then you would have a smoother curve and so on. We call that the normal distribution, and so on. Okay. So anyways, now it's time for me to go back. I wanted to quickly talk about the class midpoints to highlight to you how we could use that in a graph. Okay, here is a picture, a collection of pictures that shows you some of the common distributions. Okay, so you see this green graph. You know, it starts slowly and then rises and then falls down slowly, right? So this is a bell-shaped graph. We love this because in reality, most of the events, because if you collect a lot of data values, not just a few but many, it will most often conform to this bell-shaped distribution. So your histogram, you know, when it helps you to see the shape, and if it is a bell-shaped graph, then we call that as a normal distribution. Okay, and so meaning you are now you know, locating this distribution, this data set, to come from a certain family, and in this case that family is the normal distribution family. Now if your bars are almost of the same height, right, it's again in reality they're not going to be exactly the same height, but almost the same height, so you can kind of model it because the heights are same, constant, they're uniform. This distribution, if something looks like this, it belongs to the family of uniform distribution. Now if your histogram actually looks like a bell graph, right? This does look like the bell, the blue one here. But then you see that it's not sitting right in the middle like the green one, right? So you have the ends tapering and on the left and the right, with the majority of the graphs sitting in the middle, right in the middle of your graph. But here it is more the bulk of it is on the left, and the right kind of tapers more. And in the brown graph, it's the other way around. Bulk of the data values or the bars lie on the right end, and the left end tapers off. So we call this the skewness. It's skewed. It's gone askew, right? So we talk about that in these graphs. So here's a graph that shows you the bell shape, right? More or less the bell shape. So if you can trace this with the symmetric distribution of the bell shape on the left and the right, we know that it's not skewed. But if you have that symmetry thrown off slightly, we call it, or we say that it's skewed. Okay, so let me provide that definition here for you. So skewness right, it means that it's not symmetric, because a bell-shaped graph is symmetric. So that's how you'd notice that even if it's got the bell shape, is it symmetric? So extends more to one side than the other. So in skewness, we have the left skewed to the right and skewed to the left. So for this, I have an easy way to help you remember. Okay. So now, if you have a distribution, so between this blue and the brown, okay, say you don't have that description at the bottom, because that kind of tells you if it's the right or the left. Say you don't have that. How do you know if it is left or right? Because it's actually confusing. Because when it says skewed to the right, the whole thing is on the left, and it's actually the other way around, right? When it's skewed to the left, actually the whole thing's on the right. But what they're saying is it extends more to the right in the right skewed table graph, and it extends more to the left on the left skewed graph. So a quick way to remember that is to look down at your toes. Okay, so if you look at your right foot, your big toe is the tallest, and then the rest of the toes kind of taper more to the right, right? So they kind of extend more to the right. So that means it's right skewed. Your right foot is right skewed. It's skewed to the right. So I'll just say toes on the right foot. Now if you look at, of course, the brown one, it says it's skewed to the left. So look at your left leg. Your left leg has the big toe on the rightmost end, but the other toes are reducing in height, and it's tapering more on the left, right? So that means it's skewed to the left. So toes, so look at the way it is distributed. So those are like your histograms in your body. So toes on the left foot tells you that it is skewed to the left. Okay, so those are quick ways for you to remember. And so we kind of finishing off with this with the concepts in this chapter. Well, I do have another video from chapter 2, and there I will go over doing these problems using the calculator. Okay, so doing these problems and some graphs, all of those things in the calculator. So I'll see you in the next video. All right.